The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, welcome into today's webinar. This is Stacy at RioSense. Thanks for joining us today. I hope everyone is doing well out there. So today's topic, we've actually discussed this topic in the past. I think if you're interested in reviewing that was done in October of 2019, I believe. You can find the previous webinars on our website, or if you have some trouble finding them there, you can certainly contact us and we'll help you out. However, we did want to bring this topic back and use it to do some analysis on some new data that we've recently acquired. And we did this because we think it's an interesting topic, it's quite valuable, and then it's also, you know, using this analysis that we've discussed previously to look at new data, it kind of is testing the validity of it and seeing how valuable it is. So what we're going to discuss today in more detail then is we have some new shear rate dependent viscosity data on concentrated protein solutions, and these are exhibiting non-Newtonian behavior. So as you know, if you've been with us, non-Newtonian means that the viscosity is shear rate dependent. And what we're going to do is we're going to perform this scaling analysis that we've done in the past to see what additional information we can extract from the data. So viscosity versus shear rate data has very practical benefits to it. Obviously, if you know what shear rate is relevant for your application or your processing conditions, then you would want to measure in that range. But it's also, as you'll see, I hope, as we go through the webinar, it can be used as an investigative tool. And it can really help you understand what's going on in your formulation based on the components that are there. So when I say scaling analysis, let me just point this out before we get going. What I mean by this is we're going to non-dimensionalize both our viscosity and our shear rate. And if you're familiar with rheology or even more broadly fluid mechanics, scaling analyses or non-dimensionalizing variables is a very common thing to do. And the reason it is because it allows you to gauge the magnitude of competing either stresses or time scales or length scales. So if you have multiple events or things contributing to the system, then you can gauge the relative magnitude of those. And so that's going to become more clear, I think, as we do this scaling analysis, particularly when we're looking at relevant time scales in a concentrated protein solution. So with that background, let's go ahead and get started. So the first thing I wanted to remind you of, and then also here's where I'll introduce our new formulations that we're going to analyze today and how they're different than the ones we've done in the past. So I want to emphasize, and we re-emphasize rather, because we bring this up a lot, the connection between formulation and rheology, and in our case, specifically viscosity, but rheology in general, it certainly applies. So what happens when you're formulating a complex fluid, and in this case a protein solution, and you're varying the components that are in the formulation or even the environment that the formulation is experiencing, and we'll talk about temperature impact today. What's going to happen is you're going to change the way the components in the formulation are interacting. And as these interactions can change, then the microstructure of the formulation can change. And by microstructure, I just mean that's the common term that we use to describe the spatial arrangement of the objects in solution. And so you can see my diagram here is showing that, you know, we have these primary objects that I'm representing as spheres. And in the case of an attractive interaction, which proteins are inherently attractive, and you can, by adjusting formulation, adjust the relevance of that. These will then, the structure will evolve such that you have clusters or aggregates where they're grouped, these individual primary units are grouped together. And so this then is what I mean by microstructure or spatial arrangement. So the interactions, so the formulation impacts interactions, which interacts how these things arrange in solution, and then that all in turn is reflected in the viscosity measurement, specifically viscosity as a function of shear rate. So this is why we feel that the viscosity is a good investigative tool, because it is so dependent on the interactions and the microstructure that evolves from those interactions. And then if we look at viscosity, then we can and interpret from the viscosity how things are interacting and how they're structuring. Then we can go back and see what in our formulation could possibly be contributing to this type of interaction and structure. And then, you know, it guides us and lets us formulate with intention to develop a formulation that does what we want, rather than just sort of a brute force, shoot in the dark kind of thing. This is where we see the value here. So what we're going to do today, in the past, if you go to the past webinar and some of our app notes that we've written that complement that webinar, we looked at a lot of variations in types of salt and salt levels, or ionic strength of those salts, to sort of see how our rheology would vary and how we could relate that to the what's generally referred to as salting in or salting out of the proteins. So today, however, we wanted to look at other variations in the formulation beyond just the salt type and ionic strength. And so we're going to do two sets of data today. We're going to look at adding an excipient. In this case, it's going to be arginine, which is one of the individual amino acids. And this is a common excipient to add because for certain antibodies or proteins, the addition of arginine will actually reduce the viscosity, which is what people often want to do when they're formulating for something that is intended to be injected. So we're going to see how does our rheology reflect the addition of the arginine, and what can we interpret from our rheology about the impact of arginine on the interactions and the microstructure. And then also we're going to look at temperature, because another common thing we've realized from our customers is that when you work with the formulation, you don't only work with formulation at room temperature. Oftentimes it's in cold storage and you take it out and want to start working with it before it comes to room temperature, or you may be interested in how could these properties change as they're injected into the human body. And then of course, room temperatures vary as well. So we wanted to look at the impact of temperature on the viscosity of these concentrated proteins too. And we do know that there are common trends in how temperature will impact viscosity, but it's also true, and this is particularly true for aqueous systems where hydrogen bonding is important. Temperature can change how these components interact. The obvious impact of temperature, of course, is when you cool something down, you slow down the thermal motion, and then when you heat it up, things are moving around more rapidly. But as I stated, in the case of aqueous systems where hydrogen bonding is very important for solubility and also for certain types of interactions, changing temperature can also be a factor in changing the interactions and then microstructure. So we're going to look at that impact as well. And then we're going to stick to a modest temperature range. We're not going to go so high that we denature the protein, because then we're going into a whole other sort of topic of study there. Okay, so just to remind everyone what viscosity we're looking at, I won't spend a lot of time here, but I wanted to bring it up because one of our earlier webinars this year was basically discussing how many different types of viscosity there are. And so that we don't have any confusion, I just wanted to quickly state that what we're presenting today is all steady shear viscosity, and this is the most common one. And if anyone just says viscosity, this is likely what they're talking about. And as we know, it's a gauge to the resistance to flow. And so what we're setting up in our system is a velocity gradient that is going to be perpendicular to the direction of flow. And this velocity gradient or derivative is how we define our deformation, which is the shear rate. And the viscosity is defined as the shear stress that it takes to keep this fluid moving at a particular flow rate divided by the shear rate. And this is how we define and calculate our viscosity in this case. I also wanted to take the moment to point out that because we're going to be non-dimensionalizing and essentially scaling both our viscosity and shear rate, I wanted to sort of start hinting at how we're going to go about this process and how we're going to select the exact form of the non-dimensional groups. So I wanted to point out that shear rate has dimensions of inverse time. And so when we are doing this shear rate sweep and looking at viscosity as a function of time, what we're doing is we're basically probing events that are occurring in the fluid that are occurring on different characteristic timescales. And one of the things we're going to see if we can do is if we can correlate those characteristic timescales to characteristic length scales. So I just want to sort of plant that seed that we want to think about this shear rate as probing these different characteristic timescales that are relevant in the complex fluid. And so this is why it's important to actually do the more complete experiment rather than an individual shear rate. And not to go off on too much of a tangent, but I did want to sort of mention, if this doesn't make sense to you, I wanted to make an analogy that I thought of earlier today. If you're more familiar with, for example, scattering of any sort, this could be neutron, X-ray, or light scattering, and you're familiar with looking at scattered intensity as a function of wave vector, it's a similar concept in that when you look at that functionality, wave vector has a length scale of, or sorry, rather a dimension of inverse length scale. So as you change wave vector by generally changing either wavelength of light or scattering angle, you're looking at different characteristic length scales. So when you do low angle scattering at low Q or low wave vector, you're looking at large length scales, and you're going to be identifying any sort of network formation or larger length scale in the case of our proteins aggregates. So I'll stop there. I don't want to go off on too much of a tangent, but I just thought that might help you understand that when you vary certain parameters, you're probing events on these different characteristic scales. Okay, so before we get into how we're going to non-dimensionalize and scale, I wanted to sort of show you our data and sort of set the stage, and then we'll actually go through the process. So here's our some recently acquired data that we have, and you can see this is non-Newtonian data. We're looking at steady shear viscosity as a function of shear rate in both plots. And all of these samples are concentrated model protein bovine gamma globulin at 250 mg per mil. The left plot we're looking at in one of our homemade phosphate buffers with a modest amount of sodium chloride. We're looking at the temperature dependence. And on the right, what we have is a purchased phosphate buffered saline, where we have either left out arginine, so we have no excipient, or we've added in 250 millimolars of the arginine hydrochloride. So phosphate buffered saline alone, or with a moderate amount of arginine. So back to the temperature variation. So what we're seeing here is, we can interpret this in a very general way, and you can stop there, or ideally you'd want to proceed with the analysis that we're going to do. But let's just make the general observations first. So what we can see is as we reduce temperature, we increase viscosity. So this is the most common response to the viscosity variation with temperature. Now there are exceptions to this, and we presented those in other webinars, but unless you have some sort of complicated self-assembly that is dependent on temperature, then you won't see any vast deviations from Arrhenius behavior, but that's, again, a separate topic. However, with that pointed out, I would also like to point out that as you decrease temperature, and what we'll also see is that the onset of shear thinning is shifted down to lower and lower shear rates. So we've just discussed the concept that shear rate is related to an inverse time scale, which means that lower shear rates correspond to larger time scales, which could potentially correspond to larger length scale objects. And I'm sort of hinting at things that we're going to elaborate on as we move along here. So is something changing in terms of the microstructure of our system, or is this shift just related to the fact that as we decrease temperature, we are just slowing down thermal motion? So what we're going to see as we do this scaling, we're going to identify whether or not this shift in viscosity and critical shear rate is just speeding up or slowing down of the thermal motion, or if there is some impact on the interactions and then the resulting structure that occurs from that. And then on the right side with the arginine, so as I stated before, it's quite common to add arginine with the purpose of reducing the viscosity. So we see that we do drop the viscosity with the inclusion of arginine into the formulation. And we also see that when we drop the viscosity, we do have a shift in the critical shear rate to higher shear rates now. Again, the question is the arginine doing something to change the characteristic length scales of the objects in solution? So the theory behind the operation of the arginine, which I didn't hint at earlier, is that it acts to prevent cluster formation or reduce it to some extent. So the presence of arginine is thought to do two things: screen electrostatic repulsions, and then also potentially screen, to use the same type of language, screen hydrophobic interactions. It's sort of hand waving at the moment, but we do know from data it does reduce the viscosity, and from complementary scattering data that it does do some shifting in the cluster or aggregate size. So here's the data that we have, and now we want to sort of identify how are we going to scale this data to answer some of the questions that I posed about why these changes are occurring, and can we pinpoint in some more detail what's happening. So to start, what I'm going to do is we're going to first have a quick discussion to identify how we're going to scale the viscosity axis. Okay, so to get to that point, what I wanted to do was have a qualitative discussion on what viscosity versus shear rate is telling you for this type of system. So again, I've presented this is just some other concentrated protein sample data that I have where we're looking at viscosity as a function of shear rate. And what we see commonly with these systems, so long as we don't have something that is gelling, is we see what we refer to as a low shear or zero shear plateau. We see an onset of shear thinning at some critical shear rate, a shear thinning regime, and ultimately, if we were able to get to rates high enough, this is beyond the capability of our instrumentation, and in many cases, most types of instrumentation. But if we could get to high enough rates, then we would enter into what we refer to as the high or infinite shear plateau. So let's start down here with qualitatively, why do we even see the existence of a low or zero shear plateau? And the reason is that when you have these, and I think, when I present this, I'm going to present it in the specific context of proteins, and also interpreting proteins as being analogous to a colloidal system. And we'll talk a little bit more about that in a moment, but when I do this, I'll do it in that specific context. So what's happening when you have these macromolecules like a protein molecule, there's the ability or the possibility that what we refer to as a restorative mechanism exists on the molecular level that's acting to resist the deformation in the equilibrium structure that's being imposed by this externally applied flow field. So let me try to say that in a little simpler fashion. You have these molecules in aqueous solution, and you're opposing some external flow field. And prior to imposing this flow field, they had an equilibrium structure, and they liked being in this particular spatial arrangement. It was sort of it was the minimum energy. Now, however, you're coming in and trying to disrupt it. Okay, but it has the ability to say, no, we're not going to, be pushed far from equilibrium, and we have the ability to resist this external flow. So, there is this, what we refer to as some restorative mechanism that's acting to maintain something that's near an equilibrium state. And because we're talking about these larger macromolecules like the proteins, then they have the ability to do this up until a certain point. And what happens when they're resisting this flow field and its drive to move it from equilibrium is it generates what we refer to as a thermodynamic stress. And thermodynamics is just implying that these restorative mechanisms or this resistance to the deformation is coming from non-hydrodynamic or thermodynamic forces. And we're going to go into a little more detail on what some of these thermodynamic contributions can be, but that's the nature of that language. And so what happens then, however, so we have this plateau. The plateau exists as so long as this mechanism is effective. And then at some point, however, as we ramp up the shear rate higher and higher, at some point there's going to be this tipping point, and the external flow field is going to start sort of dominating the situation. And this is where we see this critical shear rate or the onset of non-Newtonian or shear thinning behavior. And this is where the shear flow is overcoming these mechanisms that are acting to maintain the equilibrium structure. And then as we go higher and higher in shear rate, then we ultimately get to this high shear plateau where now the structure is very far from equilibrium because we basically wiped out anything that was trying to keep it there. And this is the region where we say that the hydrodynamic interactions dominate. And the hydrodynamic, when we use this terminology, it basically just comes from the fact that we have these objects, these proteins or particles that are dispersed in a fluid. And this fluid has some finite viscosity. And it's distinct. You can't look at this as if these molecules are dispersed in some sort of inviscid fluid, such as air or vacuum. The fact that they're in a fluid that has a substantial viscosity imposes certain interactions into the system. So you can think of this as, if you take your hands and you stick them in a sink filled with water and you move one of your hands through the water, but your hands never actually make physical contact. They will interact with each other. You'll know that your one hand is moving through the water because it will disrupt the flow field around the other. So that's what we mean by hydrodynamic interactions. We're not talking about the thermodynamic interactions where you have possible contact. What we're talking about is the influence of the fluid environment on one object due to the motion of the other. So you're interacting through this viscous fluid. So you can never eliminate that, no matter how high in shear rate you get, because you're forever having these molecules in a fluid. So that's the transition from the thermodynamically dominated down here in the low shear region to the hydrodynamically dominated in the high shear region. Okay, so I understand that sometimes this language is very specific, but hopefully you can think about those ideas and when you're looking at this type of data, have a different view of it and deeper understanding. Okay, so now with all of that, now we want to say, well, from this knowledge of what we've just discussed, how can we use that then to decide how we're going to scale our viscosity axis? So what we know is then that this difference here between the zero shear plateau and the high shear plateau is a gauge of these non-hydrodynamic or thermodynamic forces that exist, or stresses, and the degree of structure or microstructure or spatial arrangement that exists due to them, and what sort of resistance to the flow that is offered by the system. So our viscosity scaling, then, what we want to look at is, as we increase in shear rate, we want to see how these thermodynamic stresses are overcome by the shear flow and how the structure is broken down. So the ideal scaling then would be the viscosity minus the high shear plateau divided by the zero shear plateau minus the high shear plateau. So what this would be is, obviously when you're in the low shear plateau region, this ratio is 1. And then as you ramp up shear rate, you're looking for the point where it drops below 1. And that's what I meant by looking at how these thermodynamic stresses are being overcome and how the structure is potentially then being broken down. However, because we don't have access to measure this plateau, the next best thing would be to substitute the buffer viscosity for the high shear plateau viscosity, which in practice generally works equivalently. So this then will be our viscosity scaling, and that's the rationale for it. So sorry for the long explanation. Okay, so now we're going to move into, we have an understanding then of how we want to scale the viscosity and why. Now we want to think about how we want to scale the shear rate axis. So now we're going to take a little bit of time to clarify that. So again, I had mentioned earlier that we're going to view the proteins as a colloid. Now a lot of people don't like this, and I do understand that it's not a one-to-one comparison. There are challenges with proteins that you don't have for traditional colloidal systems, but I'm not saying they're fully identical. I'm saying there are certain features of the colloidal interpretation that are absolutely valid, and we want to use those as a framework to interpret our protein data. So one of these things is the size range that the proteins and colloids fall into, and this is roughly a nanometer to 1 micron in diameter for the diameter. Now, this means that these objects are small enough, so the upper bound on this length scale range is such that these objects are still small enough to undergo Brownian motion. So Brownian motion is still relevant. So these objects are still going to bounce around and diffuse due to thermal fluctuations that are occurring in the solvent. So Brownian motion, just another word for diffusion. And so this Brownian motion is actually one of these restoring mechanisms that I discussed. And this is what can generate the thermodynamic stress that contributes to both the magnitude of the low shear plateau and then the onset, where will this critical onset of shear thinning occur. And so this is going to be important, this concept of Brownian motion, and it's going to be important when we talk about non-dimensionalizing the shear rate. Okay, so then the other idea from colloidal science that we want to adopt is sort of what the opposite limit here. So we talked about the upper bound allowing Brownian motion to remain relevant, and the lower bound is going to be these objects still have to be large enough to be distinguished from solvent molecules. So then what we do is we treat the solvent and all the other small components like salts and low molecular weight excipients as essentially a continuum. And then when we interpret the data, we don't worry so much about the tracking the individual behavior of everything in there, like the salts and the low molecular weight excipients. We view this as what's referred to as a pseudo one component system, and we incorporate the influence of all these small molecules by looking at how they will impact the pair interaction potential. Pair interaction potential we're going to go over in a second. This is just how do we characterize the interaction between these proteins that are interacting on a pair level. Okay, so let me think here for a second and make sure I said everything I want to say. Yes, I think so. Okay, so now we've introduced the idea of, we know how we want to non-dimensionalize our viscosity. We've introduced the idea of one of these, if we view the proteins as being analogous to a colloidal system, we've identified one of the potential generators of a thermodynamic stress, which is acting to restore or maintain the equilibrium state. And this is the Brownian motion, or just diffusion of these objects in solution. And so now we want to tie that into how is this Brownian motion relevant to the microstructure of a protein that could have variable interactions between the components. So now we want to talk about we want to think about these, how we represent these pair interactions, or protein-protein interactions if you prefer. It's a common way of saying it. And now we're talking about what we would consider thermodynamic interactions. We're not talking about the hydrodynamics, and I'll give some examples of what these could be. And then this impacts how these orient, how they structure. So generally when we look at how the proteins or particles are interacting, we classify this with this, what we refer to as the interaction potential, and we look at how this varies as a function of separation between the two objects. So R minus 2a is just this spacing between the centers of the object minus so let me just more simply state this. This R minus 2a is basically surface-to-surface separation of some object which we're representing visually as a spherical object. And if you, it's typical to use the interaction potential because of many theoretical considerations. But if this isn't foreign to you, you can, and something such as interparticle force is more clear, then force is just equal to minus the derivative of the potential. But what we know then is that, when we look at potential interaction potentials between proteins, we know that we can have what is referred to as repulsions, and these are going to be positive in sign. And then we can also have attractions, which will be negative. And the repulsions are going to act as some sort of stabilizing barrier and give you kinetic stability. And they'll prevent the aggregation or cluster formation of these objects. So when you have a substantial repulsive barrier, then you're more likely to have these primary objects dispersed in solution and remain that way for an extended period of time. And the stabilizing barriers, one of the common ones in proteins, are electrostatic repulsions. So proteins are generally charged, and you can adjust the exact magnitude of that charge by adjusting pH, and then also adjust it by adjusting ionic strength to adjust the screening of it. But in general, then, if you have a substantial repulsion, then you'll have these primary units. However, because proteins we know are inherently attractive, and you can then get aggregation to various extents depending on, again, the formulation and what kind of potential barrier you have. And so as you adjust the formulation, the point I really want to make here is as you adjust the formulation and you adjust either the magnitude of this repulsion, which is actually to stabilize and maintain mainly primary units, as you adjust the formulation, then you can adjust the height of this, and then this then can lead to, if you're reducing it, then you have more likelihood that these primary units will fall into clusters or aggregates. And so this is what we mean by microstructural changes. We've now gone, by changing the formulation, from something that's dispersed, stable, to something now that's starting to group up in clusters or aggregates. And the point I wanted to make here is that when you see this change in the formulation, which leads to a change in the interactions and then potential microstructure, you can see that as you go from something stable with these primary units to something with attractions and aggregated or clusters, now we're changing the characteristic length scale of the objects that will be diffusing around in the solution. So this is where we see where if we're looking at the Brownian motion and how this is trying to restore the equilibrium state, how the nature of the Brownian motion will change if we are changing the microstructure and going from a different extent of aggregation. Okay. All right, so with that in mind, let's go into some more detail about how we're going to rescale our shear rate. So now what we have here on the right-hand side is the data that we looked at originally. On the top, we have the temperature variation, and on the bottom, we have the with and without the addition of the amino acid arginine. And we've already rescaled, as we discussed, our viscosity on the y-axis, and now, but we still have the shear rate on the x-axis unscaled. Now we want to, with all the information that I just kind of dumped out there on you, we want to try to decide what's the best way then to non-dimensionalize or scale shear rate so that we're getting something that's informative to us. So we originally talked about from the very beginning that shear flow has dimensions of inverse time. So if we want to identify a characteristic time scale of the shear flow, then this is very straightforward to do, and that's basically just 1 over the shear rate. And again, this mechanism, the external flow field, is acting to perturb the equilibrium state into some non-equilibrium state. So it's acting to disrupt the system. So now if we're thinking, okay, now we have the shear flow, which we can very easily view as a time scale. then what do we want to do when we're trying to characterize this restorative mechanism? One of these mechanisms, one of the dominant mechanisms, being the Brownian motion of the characteristic objects that we have in solution. So what we want to do is we want to characterize some time scale associated with the Brownian motion of these objects, so that we can then compare it or balance it with the time scale associated with the shear flow. So that's what we're doing here. So we're looking at Brownian motion, and just to emphasize again, this is the mechanism that's acting to restore the equilibrium structure and keep it from being too far knocked out of equilibrium. So what then is this Brownian or diffusion time scale? So tau sub b is going to be the length scale squared divided by some sort of short time self-diffusion coefficient. So L squared in this case, because as we've mentioned, depending on the specific nature of our system, we can have either primary objects or we can have clusters of objects. So we're just going to define in general some length scale L, which is going to be 2 times L would be the diameter of a cluster. And in theory, this cluster could have varying numbers of primary objects, or it could, in the case of a very stable situation, go to the limit of the radius of the primary unit. But this will define our Brownian motion timescale or diffusion timescale, and this just comes from basically saying that what is the time that it would take this object to diffuse a distance on the order of its size in this fluid with some particular viscosity. So that's where this comes from. And now we need to know then how are we going to represent this effective self-diffusion. So in the case of infinite dilution, you would just use Stokes-Einstein. However, because we're at 250 mg per mil, which is a very concentrated system, that's not entirely appropriate. So we want to somehow account for the fact that the motion is hindered due to all of the neighbors in this concentrated system. So we're going to define basically an effective self-diffusion constant, where what we've done basically is just replaced the viscosity of the buffer with the low shear plateau viscosity. And this is a common, almost sort of effective medium type approximation to account for this hindrance in motion due to the neighboring objects. So this is then how we're going to define our Brownian motion timescale. So the first thing I want to point out is now we can sort of kind of see how the length scale of the characteristic length scale of the system is going to come into play. We can see it's going to come into play here with this Brownian motion timescale, and it's going to, depending on the extent of aggregation, it's going to increase or decrease the timescale Brownian motion. And ultimately, what we're going to see is we're going to compare that timescale with the timescale of the shear flow. But I wanted to point out one more thing before we move on to the full analysis. And that is, if you look at the short time self-diffusion coefficient, what you see is that it's not only the length scale of the object that's diffusing that's relevant, but we have this factor KT, so Boltzmann constant times temperature. And so we had noted before that one of the things that occurs when you change temperature is you change the when you reduce temperature, for example, what you're doing is you're slowing things down, and when you increase temperature, you're speeding things up. And so this is where the temperature impact comes into play with the diffusion. So I had brought up, originally that when, we're looking at the temperature dependence, we have to ask what portion of this change in rheological behavior is coming just from temperature, and what is coming from a potential change in aggregate structure due to a potential change in the interactions that might occur due to, for example, changes in extent of hydrogen bonding. So I wanted to point that out there just so you understand why, it wasn't immediately clear what was fully responsible for this variations in rheology with temperature change. So what we're going to do is we're going to say, let's then rescale our shear rate by calculating what we call the Peclet number. And this is basically just taking a ratio of these two time scales, the Brownian motion time scale and the time scale associated with the shear flow. And so we can calculate that out knowing what we have here as our expressions for the two time scales. And just to sort of qualitatively think about this Peclet number, you can imagine then that when Brownian motion is very rapid and on a time scale much shorter than the, or smaller than the shear flow time scale, then Peclet number will be small. It'll be less than 1. And this is the region where the Brownian motion, because it is occurring so rapidly, which corresponds to a small time scale, is able to resist the deformation due to the flow field. However, as you increase the shear rate and then consequently reduce the shear flow time scale, then this Peclet number will move towards 1 and then ultimately get larger and larger as shear rate increases and increases. So to sort of look at the tipping point to see where Brownian motion is starting to fail and being overtaken by the shear flow, we're going to look at a Peclet number, sort of a characteristic value of somewhere around 1. So because we don't know what this particular, one of the things we're looking to extract from our analysis here is what is this characteristic length scale and how does it change with my different formulations. So to get an estimate of this characteristic length scale, we're going to perform this scaling of the shear rate, converting it to Peclet number, and we're going to adjust L for each sample such that the onset of shear thinning occurs at a Peclet number equal to 1. And so again, just the rationale for this is that's sort of the Peclet number equals to 1 is where these two time scales basically equal each other out. And as we move past that, then the shear flow is going to dominate, and we should expect to see the onset of the shear thinning and non-Newtonian behavior. So that's what we're going to do. And so just to, emphasize again, before we did the analysis, it wasn't clear. I have my question mark up here. It wasn't clear that these shifts in the onset of shear thinning, particularly for the temperature dependence, was related to a shift in the length scales that exist due to differences in aggregation, or if it was really just the temperature speeding things up or slowing them down. Okay, so with all of that, finally, here we go. We've actually scaled the data after 45 minutes. So now what we have is our scaled viscosity and versus Peclet number. And what we can see is when we do this particular scaling, we're able to generate a viscosity master curve. So now, prior to this, I had the two groups of samples where I had the temperature variation and then excipient impact on separate plots. But just to show you what happens when you actually do the scaling, we can actually put all of those, even though they're two separate systems, onto a single master curve. So this is implying or supporting the idea that we've chosen our scalings appropriately to account for competing time scales when we're looking at the Peclet number, and then also looking at the sort of reduction in thermodynamic contributions to the stress as we increase Peclet number. So the result that we have this master curve is quite encouraging, that we've chosen our scaling properly. So now let's then look and see if we can interpret some of the things that we hinted upon at the beginning. So let's start with the temperature data. So what we found when we scale this, so remember through this scaling, because we didn't have complementary scattering data or any other way of characterizing the length scale in the system, we were using this scaling to extract some characteristic length scale and see how this is changing with our buffer conditions or environmental conditions in the case of temperature. So if you look at temperature and how our characteristic length scale varies with temperature, what we're seeing is sort of within the error of this analysis, and I haven't formally developed a way of categorizing the error that we have in L as of yet, but based on some variability and ambiguity in how you choose L here, I would argue that 9.8 to 10 is pretty much equivalent as we vary temperature. So this would indicate then that the change in behavior that's occurring when we change the temperature in this protein solution is entirely coming from just the speeding up or slowing down of the motion that occurs just from the temperature change. There's no indication, because we don't see a drastic change in the characteristic length scale of the system, there's no indication that we're dramatically altering the interactions and therefore any extent of cluster formation or aggregation. So that would be one way of using this to interpret this. So we feel that we're not having any significant impact on how these components are interacting as we change temperature. The temperature change is just coming from typical Arrhenius type behavior. However, when we look at how the excipient behaves, so now we have a either no excipient or 250 millimolar arginine hydrochloride. What we see is now a real and significant drop in the characteristic length scale as we introduce this arginine hydrochloride. Now, this is consistent with the idea that the arginine is reducing to some extent the attractions that are contributing to the formation of clusters. And we're reducing, average, say, cluster size by introducing this arginine. And then this also supports the idea that it's the cluster formation, this reversible cluster formation, that does lead to an increased viscosity. Because as you'll see, when we take out when the arginine is not present and we have this larger characteristic length scale, our viscosity is higher. So just to sort of reiterate, it does appear that the parameters we're extracting from the scaling analysis are supporting the idea that without the arginine, we have larger clusters, and this is then contributing to a higher viscosity. So I think let's just take another quick view. So let me jump back here for a second. So this is in sort of tabular form, and then we see the master curve. But if you want to look at these length scales in a graphical representation, if that's more comfortable for you, what we're looking at here is what we call effective cluster volume, which is just L cubed. And this is kind of more traditional way to look at it as opposed to the individual length scale. And what we're looking at here then is this cluster volume as a function of our different, what we're varying here. So if you look at the temperature variation, you can see that there's no clear trend that we see as we vary temperature. And in fact, the variation is quite minimal and likely within the error of this analysis and how we actually select this length scale. Whereas when we look at the with and without the excipient arginine hydrochloride, we can see that there's a clear drop in this characteristic length scale and effective cluster volume as we introduce the individual amino acid, which is, it's hypothesized, as I stated, that this is breaking up clusters and reducing their size. So this is consistent with that hypothesis. So with all that, I'll just quickly summarize. And we always emphasize that doing an analysis of your data rather than just looking at it is always very beneficial. And in the case of protein formulations, although it's not a perfect comparison, I feel that adopting certain ideas from the colloidal systems is quite beneficial and helps you get a deeper perspective into what's happening. An advantage of analyzing rheology data on concentrated systems is we're not dealing with any dilution effects and breakup of reversible clusters that may happen through dilution. So we're getting a better picture of the what's happening in the concentrated state. I will point out, though, that at the moment, until we have, some more data worked out, we're still looking at things on a relative rather than absolute scale. So that's why when I present the data, I'm looking at how are things trending when we change some particular aspect of either the environment or the formulation. So with that there, I will see if we have any questions. So we do have one question here, which I'll read out so that everyone understands what I'm answering. So the question is, if you don't know if your sample is non-Newtonian early on, could this be a problem? Could this be detrimental? So the question is, this is, I guess I would say, a more practical implication of doing a more thorough analysis and looking at shear rate dependence. And I would say, if you have no idea about whether your sample is or is not non-Newtonian, and you have some idea of shear rates that are relevant to you, whether that's for processing or application, then I think it could be a problem, because if it's non-Newtonian and you're measuring at a shear rate that is very far from what is relevant to your application or processing, then you could make predictions that are quite frankly meaningless. So it could be detrimental if you don't understand whether your system is Newtonian or non-Newtonian, and that's a very practical side of a thorough analysis. Okay, we have another question. Okay, so we have a question relating to, so when I showed you the data that for these particular groups of samples, we had a very clear low shear plateau value, and then we saw a very clear onset of shear thinning behavior. And the question that is being asked is, if I do not have a extensive low shear plateau value, can I do this type of analysis? And the answer is possibly. And by that, I mean, if you're very close to the plateau, so if all you have is maybe power law dependent data where you're only in the shear thinning regime, I would say then this analysis is going to be difficult or impossible. But if you have data that's approaching the plateau, and so you can see an inflection in the data moving from the power law to some inflection looking like it's plateauing, then I would say what you can do, and what we have done internally, is you can use some of the various models for viscosity versus shear rate. So one of these is the Cross model. A very popular one also is Koro-Yasuda model, and there are others. You could utilize these to basically estimate what your behavior would be as you move towards the plateau, and sort of substitute some of your data for the extrapolation from that model. But again, I would only recommend that if you have some sort of indication that your data is plateauing, and I would not recommend it if all you have is power law data in the midst of the shear thinning regime. Okay. So I'll just wait a couple more minutes in case there are some questions, and also point out that if you're either shy and you don't want to ask questions, or if you just happen to think of questions later, everyone who signed up will get an email from Grace within a week or so with both the recording of the webinar and the slides for the webinar. So you can review it again. If you have questions later, then you also have our contact information. You can certainly email one of us, and we'll get to your question. We'd be happy to answer it. So we understand that sometimes these things don't sink in until later. So I just wanted to point out that you will get a copy of everything, and then we're, along with contact information, so that you can send questions at a later time if that's beneficial to you. And again, I'll just say one more thing, give you just a little bit more time in case you have more questions, and then I'll let you be. If you'd like to go look at with a previous discussion of this topic where we analyzed a different set of data, go to our website. Like I said, I think that's October 2019. Also, if you can't find it, you can contact one of us, and you can sort of see how we discussed it at that time. So it's the same topic, same general information that we're presenting, but because I never rehearse, I never say things quite the same way each time. So, my verbiage would be a little different, and maybe if something was a little confusing this time around, you might want to go listen to that and see if that presentation is a little better for you. And plus, it's a different set of data with a different look at a different buffer environment and how it impacts the proteins. Okay, so we're approaching an hour, so I've taken up enough of your time. So thanks again for joining our webinar, and we will have another one in August. I think our plan is to do something related to protein stability and how viscosity can help you understand the stability of your protein. Again, we're using then viscosity to interpret what's happening on the microscopic level in terms of the structure of your system. Okay, so thanks again, and take care, everyone.